This is analysis of time series, chapter 9. We're going to work through a case study looking at an association between unemployment and mortality, looking for evidence from time series data, whether there is an association, whether it's positive or negative. So we'll start by looking at the problem and some data. We'll have to do a detrending exercise because we're going to be interested in fluctuations around a trend. And then this will give us an example of doing the kind of hypothesis testing regression with ARMA errors that we've been studying in previous chapters. Interpreting these results will give us reason to think about association and causation, an important statistical topic, but we'll be looking at it in the context of time series analysis. And that will also move on to looking for dependence in bivariate time series, cross-correlation, the cross-spectrum. These are useful exploratory techniques. And then we'll look at some other analysis that can be used to flesh out the case study. So historical investigations linking business cycles to mortality perhaps start off with an early report by Ogburn and Thomas, 1922, which observed the possibly surprising result of so-called procyclical mortality, where death rates are statistically above trend when economic activity is above trend. And so this shows, if it exists, if we find that that's what the data tell us is going on, then a key measure of population health is worse in economic booms than in recessions. Now, one reason this may be counterintuitive is because the trends tell us a different story. So both the economy and life expectancy have grown over the last 100 years or so. So that might make you think that economic growth and life expectancy go hand in hand. There's certainly some truth to that. However, these phenomena have not always occurred simultaneously. There are some examples where they happen at different times. So, for instance, 1950 to 1980, there was rapid growth in life expectancy in India and China, relatively slow economic growth in those periods. And then economic growth really picked up, but improvements in life expectancy slowed, which suggests that maybe the association isn't as strong as one might imagine. It's controversial because it has political implications, and that means that economists and epidemiologists have argued both sides of the debate, and it's really a debate about time series, so it involves time series methods. Here are some of the potential implications of procyclical mortality that fuel the controversy. So if our goal is population health and happiness, how much should our policies focus on gross domestic product growth? Well, that really depends on the link between GDP and broader population welfare. If the statistics showed that economic growth is the critical engine for other improvements in living conditions, then that would put you in a pro-economic growth mindset. On the other hand, if you discovered that there are other major factors in improving living conditions and economic growth was only one political consideration, then that's a different perspective. And so let's see what the data say. So we're going to need, we're going to need a measure of human welfare and a measure of the economy. For human welfare, we're going to use life expectancy. So that's a very clear-cut measurement. You're either alive or you're dead, and it's well measured in official statistics. And so we're going to use data from the human mortality database. It's in a file, life expectancy USA.csv, and the file has the full source in it. So you can see here the columns in the file. There's year, E0F, E0M, and E0. E0 is so-called life expectancy at birth, abbreviated to LEB for civilians. E0F and E0M are the same quantities for males and females. We're going to focus on the total life expectancy at birth. So life expectancy at birth is not the expected duration of life of somebody born today. What it is, it's an actuarial calculation for a fictitious individual with mortality rates at each age matching current estimates of age-specific mortality for the current year. So you imagine somebody who goes through all their aging today at the current mortality rates. So rather than trying to estimate how long somebody born today would live, what it does is it combines all age-specific mortality rates into one interpretable number. So it's a very standard single number to represent welfare of a population. For the economic data, we're going to look at the unemployment figures from the Bureau of Labor Statistics that we looked at in Chapter 8. Unemployment's just one component of the state of the economy. You could consider other measurements. We're going to consider unemployment. We're going to write EN for life expectancy and UN for unemployment. And this puts us in a position to start the data analysis. I guess the first thing to do is to look at the raw data. Well, the life expectancy keeps going up. There's a clear trend from 1950 so to 2020, and the unemployment goes through periods of high unemployment and periods of low unemployment with some slower trending patterns around that. And we're interested in changes over business cycle timescales once trends have been removed. It's really hard to conclude relationships from trends because anything that trends together could explain each other. Whereas if you have cycles either cycling together or not cycling together, then it gives you some sort of evidence for at least shorter term causation. So we're going to detrend. What we're going to do in this case study, we're going to detrend the way many econometricians do. We're going to use the Hodrick-Prescott filter, which has this form in equation 1. If we have a time series yn star, then we can smooth it to a series Sn star following this recipe. We want to find the smooth values should minimize the sum of squared differences to the data, with also a penalty corresponding to the sum of squared second differences of the smooth multiplied by the smoothing parameter lambda. In non-parametric regression, the HP filter is known as a smoothing spline. And we'll also see later in the course that it can be viewed as a state space model. Then you have to decide what value of lambda to take, and a standard econometric value for lambda for annual data is lambda is 100. So we're going to use that. And we're going to use the R implementation of the Hodrick-Prescott filter in the R package M filter. There's a function HP filter that does the job. And using this Hodrick-Prescott filter, we can define the HPD trended life expectancy and unemployment. and here's the code to do just that. We're going to want to view these things. In this particular case, it's convenient to plot two time series on a single graph. That's not always advisable because measuring different things, so putting them on the same axis may remove clarity, but I think in this case it adds clarity. So here's some code to do that, but let's look at the plot. So what do we have? We have detrended unemployment in black on the left axis, detrended life expectancy at birth, red on the right axis. And I think just looking at these two things, it looks like they cycle together. Let's see what that means. That means high unemployment corresponds to gains in life expectancy. That means gains in life expectancy happen during recessions, according to this association. Now, the pattern may look evident to the eye, but it's not so amazingly undoubtable that you don't want to make a formal statistical test to check that your eyes are not deceiving you. So let's go do that. And a regression with ARMA models is a natural way to do that. That is a statistical test that's valid in the presence of dependent errors. So let's write down a regression with ARMA errors model where our model for life expectancy, which we're going to use EN, big EN for the random variable in the model, depends linearly on the unemployment with a Gaussian ARMA noise. I'm going to go through using an ARMA 1.0, an AR1 model. In the supplementary analysis, we consider other possibilities. So we can fit the AR1 model, and here we go. It's called A0. It's just fitting regression with ARMA errors, exactly the model, the code to fit model 2, that equation 2 above. And we see that the coefficient for the all the coefficients are significant, and the coefficient for unemployment is significant and positive. And the first pass at a statistical test is to take the coefficient, divide it through by the standard error. Remember that standard error is computed via observed Fisher information. The ARMA function numerically calculates the derivative of the second derivative of the likelihood and uses that to calculate the Fisher information, which gives a standard error, and then divide through the estimate by the standard error. That gives us a Z statistic, which is 3.94. Well, that's a whole lot bigger than the usual Z test for statistical significance, which is around about 2. So we think it's quite clearly significant. We can also do a likelihood ratio test. We want to compare the model with unemployment as a covariate against the model with no covariate, and we can calculate the likelihood maximized over each of those models, and that gives us a likelihood ratio test, which then, using the Wilks likelihood ratio approximation, we take twice the difference of the log likelihoods, compare it with a chi-squared on this number of degrees of freedom. There's a 1 degree of freedom difference because the basic ARMA model just has one parameter for the mean, which is a constant mean, And the model, including unemployment, has two parameters, an intercept and a slope for the coefficient of HP. Okay, this gives a p-value of 0.00018. So we're pretty sure that there's a positive association between detrended unemployment and detrended life expectancy. The next question is where we go with that. What do we conclude? Much of time series analysis, not all of it, but much of it is based on observational studies. A time series is often something that somebody has measured. It's not a consequence of experimental perturbations. It's just a consequence of observing something. And so the interpretation of observational studies is often relevant to time series analysis. Well, the first step in being careful is often to talk about association rather than causation. Often you would like to talk about what has caused something, but what you can immediately measure is what's associated with something. And so we should think about the different possible links between association and causation. So if you measure two things, X and Y, and they're associated, it could be X that causes Y, it could be Y that causes X. It could be that they're both caused by a third variable, Z. Z is some unmeasured variable that's been or measured but omitted from the analysis. Z is called a confounding variable. And apart from 1, 2, and 3, really the only other possibility is that the association is a coincidence. And that is exactly what the hypothesis test does. And a statistical hypothesis test will rule out the possibility that it's a coincidence, but it can't readily tell you about which of 1, 2, and 3 might be going on. Well, in this particular case, and every data analysis, you need to use your reasoning about the subject matter or your understanding of the subject matter to try to make sense of the statistical results. And in this case, it's not considered plausible that mortality fluctuations drive economic fluctuations. That would be the reverse causation possibility. In many other situations, if somebody tells you it looks like X causes Y, you can say, well, are you sure it's not Y causing X? And I guess at some point we have to rely on what economists and epidemiologists consider plausible. They don't consider the reverse causation plausible. Confounding variables, there's a lot of them. And a way to think about that is that unemployment, we're not really thinking unemployment is necessarily explaining mortality itself. It's a proxy variable for everything else going on in economic fluctuations. And so, yeah, we're not saying increased unemployment is directly causing reduced mortality, because it could be any other cyclical economic activity is confounded with unemployment. Okay, so another potential confounding variable is lagged economic activity. Let's think how that would work. So we found a possibly slightly counterintuitive relationship that high unemployment is associated with gains in life expectancy. And theoretically, that could be just because the gains in life expectancy are a delayed result of the previous economic boom. And so to talk about that, we have to investigate lag relationships between two time series. And that's what we're going to do now. A starting point for that is the sample cross-correlation function, the sample CCF. And for two time series xn and yn, the sample cross-correlation function rho hat xy of h is the correlation between x and y lagged by h and the square root of the variances. Here, I haven't normalized top and bottom by 1 over n. That would cancel out. So the sample cross-correlation function, if you have a bivariate stationary time series model, estimates the theoretical cross-correlation at lag h, which in this case would be rho xy of h is the correlation between xn plus h and yn. And this is the first time we've seen the term bivariate stationary time series model. Well, a bivariate model just means a model for a pair of random variables, x and yn. And that's stationary we have the same definitions of weak and strong stationarity that we do for a single time series. It's stationary if the joint distribution of all these things is shift invariant. Okay, let's plot this thing and see what we get. So here's the sample cross-correlation function for detrended life expectancy at birth and detrended unemployment. And what we see is that the clear, strong effect is a positive cross-correlation at lag 0. And that's the association that we saw from the plot and that we tested for in the regression with ARMA errors. We also see these kind of oscillatory pattern. Let me draw it on. And we might well think, what's up with that? Well, this pattern is relatively small. It never gets to be pointwise significant. On the other hand, it's a clear pattern, and oscillatory patterns may show up much more clearly in the frequency domain. So that's what we're motivated to look at next. And that will be in part 2 of this chapter.